Hello everybody, welcome to this summary series. Today we are going to learn very important chapter of organic chemistry that is placed in your class 12th grade, Haloalkane and Haloarene. This chapter lay foundation for the entire organic chemistry of your class 12th. By the way, organic chemistry in my opinion is one of the most logical subject that I have ever studied. Hence, the reason I have chosen organic chemistry to pursue doctorate. So I did my PhD in organic chemistry. I should tell you. So organic chemistry is the most logical subject in the sense that every single reaction is connected with another reaction, and you need not to memorize the reaction at all. I personally feel that students are afraid of, so this is the reaction I don't remember, this is the reaction that I cannot remember what to do. You need not remember the reactions at all. At first place, you need not remember. What you need to do is to understand, right? And I'm going to help you with all the theoretical as well as experimental aspects of every single reaction from today's lecture. And these notes are going to be well sufficient for your, even if your board examination, for your JEE mains examination, for your NEET examination, anything that you might be preparing for, these are going to be more than sufficient notes. You need not read anything, you need not prepare anything else, just go through the notes and you keep your NCERT alongside. Let's start with today's topic, everybody, Haloalkane and Haloarenes. So what does haloalkane basically means, and what are haloarenes, what are their meaning? That also we are going to understand in much detail, very fine detail. And my promise to you, after this lecture ends, you will be very confident that yes, today we have known to something called organic. We will be discussing method of preparation of haloalkanes, then we'll discuss its chemical properties, then we'll discuss haloarenes method of preparations, and then its chemical properties. So I have divided this session into 4 parts. One will be method of preparation, the second half will be of the chemical properties. So how they participate in chemical reactions. So before we begin, let me quickly tell you what are haloalkanes. In your NCERT, there is a general symbol R used for alkyls. And if you connect it with X part, it becomes haloalkane. Haloalkane. How is it derived? Let's start with methane. So CH4 is methane. Suppose from here I subtract one of the hydrogen and add one halogen. X is a general representation for halogen. That becomes CH3X. So from methane, I could prepare halomethane. Halomethane. So it can be let's say CH4. You can prepare CH3Cl. So chloromethane, bromomethane, fluoromethane, iodomethane. Anything that you wish, you can prepare out of all these halogens available to us. Now, if you replace R with something called AR. AR is a general symbol used for aromatic type compounds. For example, which are derivatives of benzene. Suppose this is benzene, C6H6 will be the general formula. I replace one of the hydrogen by halogen. So benzene derivative. What is this? Haloarene compounds. So we will be separately studying a chemistry of haloarenes, and we will be separately studying chemistry of haloalkanes. So haloalkanes, haloarenes, these are the two classification of the compounds for the discussion today. Let's begin with the preparation of haloalkanes starting from an alcohol. Let's say I start with an alcohol, that's CH3, CH2, OH, or any alcohol for the sake. How do we actually prepare haloalkane? Now I will be treating it with H+. Now what does H+ means? What will be the source of H+? Let's say I start with HX. What's an acid, by the way? Acid is a thing. Acid is the substance which upon added to water liberates H+, right? Anything that furnishes H+ or produces H+, once you dissolve that in water, is an acid. Once I dissolve HX in water, it is going to produce H+ and X-. You need to track all the positively charged species, all the negatively charged species, so that reaction becomes extremely simple for you. What is this thing? It is known as an electrophile. Any particle, any particular species which lacks electron is known as electrophile. What are the identification of an electrophile? There should be either a positive charge, absolute positive charge, or there should be a delta positive charge, or there should be deficiency of electron, incomplete octet. Incomplete octet. That is the identification of an electrophile. If you see absolute positive charge or a delta positive charge, or that atom has an incomplete octet, that will be known as an electrophile. So hydrogen plus has no electron. Its octet, rather its duplet, is nil, is zero here. So it's desperately looking for 2 electrons. What about this X minus? X minus, such species are known as nucleophile. The species which have excess of electrons. How do we identify them? Either they should be absolute negative charge, or a delta negative charge, or a lone pair, or a double bond, meaning triple bond, or simply we can say there is a multiple bonds present. So I'm writing double bond or triple bond. Even benzene can act as a nucleophile, right? Will you be able to identify electrophile and nucleophile? Awesome. In this reaction now, this oxygen has 2 lone pairs present and hydrogen plus is present, X minus is present. Always react an electron deficient species with electron rich species. So you people have to tell me, out of these two and this third one, which two are going to react first? Always an electrophile, which is in general represented by E plus, and a nucleophile, they two come from either two independent substances, independent groups, independent reactants, or they might be present in the same reactant. But right now we are not discussing any complicated matter. We are considering one of the component has electrophile present in it, the other one has a nucleophile present in it. They two will do gulu gulu, and eventually you will obtain a bond. You will make a bond, a covalent bond between an electrophile and nucleophile. As a result of this gulu gulu, there will be a bond made. Right, everybody? Let's try to figure out which one out of the two is an electrophile, which one out of the entire thing is an electrophile and a nucleophile. So this is a nucleophile. So this can obviously react back on H plus. But if it had to react back on H plus, why did it lose H plus at first place? Why did it liberate? Why did it produce H plus? So therefore, the reaction between the two is nonsense. Never ever going to happen. Will this X minus react with a nucleophile? Will nucleophile react with each other? No. Will an electrophile nucleophile react with each other? Yes. So I have identified this is my electrophile and that's my nucleophile. Is that point clear, everybody? Likewise, you have to do the identification of electrophile and nucleophile, and your entire journey of organic chemistry is very, very, very simple. My guarantee to you, everybody, you just have to be very careful in identifying electrophile and nucleophile. Right? Now, always remember, nucleophile attacks on electrophile. A nucleophile attacks on electrophile. So let us attack. Once it attacks, what are you going to form? There will be CH3, CH2, oxygen which has donated its pair of electron should gain a positive charge as a result of 3 bonds. Correct? And whenever there is a pair of electron also present, whenever you see their water is present with a positive charge, oxygen has formed 3 bonds, this will always leave. Such kind of groups which leaves with a pair of electrons are known as leaving group. Leaving group. Any group which leaves with the pair of electron, this is the pair of electron present, it is leaving with the pair of electron, leaving behind a positive charge is known as a leaving group. Itself will become a neutral species. Now once it leaves, what do you expect, everybody? CH3, CH2, positive charge. Now this positive charge species, this has now become an electrophile, and you had one nucleophile also present in the beginning. They too will attack on each other to finally form CH3, CH2, X. Do you understand? From alcohol, how do we actually make alkyl halide? Is that point clear, everybody? Very clear, everybody? Crystal clear? CC, is it crystal clear? Is it crystal clear? Yes? Awesome. Chaliye the next part. From halogenation of alkanes, how do we actually do alkanes? You should know that alkanes are the least reactive hydrocarbons. Least reactive hydrocarbons. Then what do? We will be trying to do a reaction Let's say I have CH3, I have CH2, I have a CH3. The carbon which is connected to one carbon from anywhere left and right will be known as having primary hydrogen. It has primary hydrogen. The carbon which has two carbon neighbors, those hydrogens present on it are known as secondary hydrogen. So this is also primary? Yes. This is also primary. Can we have tertiary? Yes. Can we have a tertiary? Yes. Can we have a quaternary? No. This is my tertiary hydrogen. This is primary hydrogen. These are also primary. This is also primary. Understood? Sir, I want to have primary and secondary, both of them in the same molecule. Let's have it. Let's have it. Let's have it. This becomes my secondary. This is still primary. Is the identification clear, everybody? The primary, secondary, and the tertiary hydrogen in an alkane molecule? If yes, then I will react it with light, H nu. You know, Planck was a scientist. He said that the light is made up of photons, and every photon has an energy E is equals to H nu. So we represent light by writing just H nu. Okay. Now this light could be of any particular wavelength for a reactant. Now you will be using X2, dihalogen. Now X2 can be, we don't use generally F2 because F2 has a very high reactivity, violent reaction it does. So we will be using Br2, Cl2 or I2. Either of the three we can use for this reaction. Okay, as a result of which you will be getting the haloalkane as the product. Haloalkane as the product. And out of the two, out of 1, 2 and these three, Br2, Cl2 and I2, Cl2 is most reactive. See, I'm not comparing it with F2. Most reactive. Most reactive. Br2 is moderately reactive. Moderately reactive. And I2 is least reactive. I2 is least reactive. So we basically do the reaction with Cl2 and Br2. The more reactive species, they will be least specific. They are going to be least specific. So what does it mean specific here? Specific means this chlorine does not mind if this hydrogen is to be substituted or the secondary hydrogen to be substituted or this tertiary is to be substituted. It will substitute all of them. It won't wait. But Br2, which is moderately reactive, is more selective. So we should write selective instead of specific. More selective. More selective. So they will select hydrogen. They will select hydrogen which one to be substituted. So hence I can say that I may result based on CH3, CH2, CH3. If you react it with Cl2, you will get mixture of product. You will get a mixture of product. Plus CH2, there is a hydrogen CH, hydrogen already present. This becomes CHCl and this is CH3. You will get a mixture, right? You will get a mixture. But when you have Br2, if you have a Br2, then it will prefer the one which is more stable. It will form CH3, CH. This in very particularly, this compound formed would be in higher amount. We also know here the tertiary one reacts in this order. The tertiary one will be more secondary than the primary. This will be the product distribution. Tertiary hydrogen will give better result to secondary and the primary one. Clear, everybody? Okay, next one, from halogenation of alkenes. Now alkenes are, let's say I have CH2 double bond CH2, the simplest alkene possible ever. If you add X2 in CCl4 like non-polar solvent, there will be anti-addition. There will be anti-addition of X and X across carbon-carbon double bond. You will obtain CH2 single bond, X here, another X here. So this is an anti-addition. So one chlorine will be towards you, the other chlorine will be inside, or any particular halogen. So you can do Br2 addition, you can do Cl2 addition. Generally we deal with Br2 or Cl2. But if you do it, the X2 addition in a polar solvent like H2O, then there will be HOX addition. You have to add X plus and you have to add OH minus. So the compound formed would be halohydrine. This represents halo. This represents hydroxy. So halohydrine compound. This will be known as halohydrine compound. You can have here HOX addition, right? HOX addition. Now this HOX can be HOBr, HOCl, HOI addition. HOI. Is this clear, everybody? Crystal clear? Sure? Good. Next, from the hydrohalogenation of alkenes, did we just discuss this? Yes, we have discussed. Now I will be discussing, this is the third part, okay, alkene. Yeah. From hydrohalogenation, I would like to do this also. Suppose you have CH3 instead of that. Let's go to that. Yeah. Hydrohalogenation, we will be adding HX. Let's have RCH2, 1, 2, 3, CH, double bond CH2. Let's take that example. And I want to add HX to this molecule. If this HX is, this can be HCl, this can be HBr, you can use HI also. We generally do not study HI, we generally don't study HF. So we will be sticking ourselves to just 1, 2 and 3. So the product formed would be CH3, R will be R, CH, single bond CH3, there will be halogen added. So I have added a halogen here and H here. This you might have studied in your books also, known as Markovnikov addition. Markovnikov addition, which is also known as a little simple M rule. But I don't like this blind definition for many reasons. Why? If I change the framework of this molecule, you need to decide where the carbocation is actually formed. That carbocation has to undergo rearrangement. Finally, you have to attach that X minus where the carbon positive charge is finally present. Am I clear, everybody? Are you understanding? Are you following my point? If you use either of the three, then you have to follow Markovnikov rule. You need to form carbocation C+. Then you have to do rearrangement. If possible, what is rearrangement? You can involve hydride shift. Then there will be methyl shift. Then there can be aryl shift. Then there can be any sort of alkyl shift. Anything, aryl shift. There can be ring expansion. There can be ring contraction. Various kinds of carbocation stability rearrangement. There can be ring contraction also. I personally love this a lot. Ring contraction. Ring contraction, various possibilities, and this actually helps you in understanding every fundamental of organic chemistry. So here you have to discuss inductive effect, mesomeric effect, resonance effect, hyperconjugation effect, whatnot. Every aromaticity, every single effect comes into this understanding of rearrangement, right? Now, if you use a combination of HCl, or I can, instead of that, I can say HBr with peroxide. Now peroxide can be H2O2. It can be benzoyl peroxide, BPO, benzoyl peroxide. It can be any other sort of peroxide. It can be perbenzoic acid. You can use metachloroperbenzoic acid also, CPBA, metachloroperbenzoic acid. If any one of it is present along with HBr, only HBr, then you are going to do anti-Markovnikov addition. Now, what's anti-Markovnikov and what's Markovnikov addition? Let me quickly help you with that. If you have RCH, such kind of unsymmetrical alkene, this carbon having more hydrogen, this has more hydrogen, this carbon of the double bond has less hydrogen. According to Markovnikov rule, if reagent AB has to be added and A has a positive charge, B has a negative charge, this positive charge goes to this carbon which has more number of hydrogen, and negative charge component goes to the carbon which has less number of hydrogen. Then the product formed would be RCH, double bond ka ban jayega single bond, and the carbon having more hydrogen receives the positive part, A here and B here. But according to anti-Markovnikov rule, we do the reverse of it. So this is according to Markovnikov, and according to anti-Markovnikov rule, the positive part, let me use the other color, the positive part will go to the carbon having less number of hydrogen, the negative part goes to the carbon having more number of hydrogen. This represents anti-Markovnikov rule. So according to anti-Markovnikov rule, the product formed would be B here and A here. I am sure now you have understood what does Markovnikov and anti-Markovnikov rule makes sense. Let's proceed to from the halogen exchange reaction. The very important one is known as Schwarz reaction. What does Schwarz reaction means, everybody? Schwarz reaction means, suppose you have R halogen and you want to particularly make RF here. It is just for the production of fluoroalkanes. You can use AGF. You can use AGF, or you can use SbF3, or you can use Hg2F2, or you can use COF2. All of these are fluorinating agent. The product formed would be RF. This is known as Schwarz reaction. Very important name relation, Schwarz reaction. If you want to study about Finkelstein reaction, starting from Rx and reacting it with sodium iodide, in the presence of a polar aprotic solvent. This is known as polar aprotic solvent. In short, PAS, polar aprotic solvent. This actually helps in increasing the rate of the reaction by stabilizing the intermediate form. So it will be RI. In general, if you want to form iodoalkane starting from RCl or RBr, then you can name this reaction as Finkelstein reaction. Very important from a laboratory perspective, from a laboratory point of view, very, very, very important reaction. I hope everything is clear so far. Right, everybody? Now let's discuss the electrophilic substitution reaction. So we need to substitute the compound with the help of electrophile. Which compounds? Arene compounds. So haloalkane compounds ka preparation is done. Let's discuss haloarenes now. Now haloarenes, suppose I have benzene ring which contains double bonds. As I already told you, carbon-carbon double bond containing species are also nucleophile. So when I react it with X2, will there be any reaction? In CCl4, compare it with carbon-carbon double bond. When I was reacting it with X2, we could do anti-addition. Right, everybody? We could do anti-addition. One of the halogen here and one of the halogen here. Can we do the same here also? Impossible. That cannot be done. Reason: it cannot be done because these double bonds are actually not at all there. They are in resonance. Due to resonance, the double bond has lost its nucleophilic nature. Now, what do we need to do instead of that? There will be no reaction, absolutely no reaction. But I want to make some halogen containing arenes. So I will be starting with X, but in the presence of FeX3. What I will do, I will add a Lewis acid. What is this Lewis acid going to do? They two are going to first react to form X2 plus FeX3 will first form FeX4 negative, or you can start with FeX2 also. FeX2, then you can form FeX3 negative, and X plus is formed. X plus is formed. You can use FeX2, you can use FeX3. All these are experimentally proven. These are experimentally proven. You can use either of it. FeX2. Clear? Now, what did we do here? Why? Plus, there is a plus. What did we do here? What's the use? What's the fun? See, earlier I was saying that the nucleophilicity of benzene has decreased due to the resonance. I somehow cannot increase its nucleophilicity, but the X2, can I increase its electrophilicity? Yes, by having absolute positive charge. By having absolute positive charge, and to create absolute positive charge, I need to take help from Lewis acid. Need to take help from Lewis acid. You can use ZnCl2, you can use AlCl3, you can use lots of examples that are, lots of Lewis acids are available, but the presence of Lewis acid is essential. Lewis acid is essential. If you do not use Lewis acid, you will not obtain haloarenes. Once you do that, the compound obtained here is halogen substituted. That's your haloarene compound. This is one way of doing that. Understood, everybody? How do we electrophilic substitution is done? This is positively charged species. I have already explained to you, anything that carries a positive charge is labeled as electrophile. Labeled as electrophile. Either you increase its electrophilicity of X2, I have done that, or you increase the nucleophilicity of benzene. That I didn't do. I didn't touch benzene at all. I just want to increase the electrophilicity of X. Clear? Now from aniline, how do we make haloarene compounds? Please pay attention here. Starting from aniline. What is aniline? Aniline has NH2 with a benzene, NH2 benzene. Amino. This is NH2 group. Now when you react it with NaNO2 in 0 to 5 degrees Celsius, the temperature has to be maintained with HCl. There is HCl also present. 0 to 5 degrees Celsius. This combination is going to produce HNO2. HNO2 is a very weak, or it's a unstable substance which produces NO+. It's a source of NO+. Please make a note of it. HONO or HNO2, nitrous acid, is a weak acid. It's unstable. It dissociates to produce NO. Okay. Now 0 to 5 degree temperature is essential. If you don't maintain that, you will not get the result. When I was studying in IIT, this was my very first practical to be done in the laboratory exercise. Very first exercise of the diazotization. This is known as diazotization. So the product obtained is having N triple bond with a positive charge here, and Cl minus stabilizes the negative positive charge. This was the very first experiment in the organic laboratory in my IIT Delhi days. Now, what do we do to this? This is known as aromatic diazonium chloride. That's basically a salt. That's a salt. We practically use aromatic diazonium salt. Alkyl diazonium salts are very unstable. So practically in a laboratory you cannot use them. So you start from the benzene diazonium salt. If you react it with CuBr, that's Cu, let me change the color of the pen. If you use Cu2Br2, cuprous bromide. If you use Cu2Cl2, that's cuprous chloride. If you use CuCN or simply CuCN, let's say, so cuprous cyanide. All these three are going to result into the substituted product, but we are interested in bromination, we are interested in chlorination. So chloroarene is produced, bromoarene is produced, and if anybody asks you what is the mechanism do they follow, it's a radical mechanism they do follow. But you need not go into the detail of the mechanism of this particular reaction, but others I am explaining wherever it is required. Now, when you react it with Ki, it forms iodobenzene. If you react it with HbF4, or one of the excellent method of preparing fluorobenzene. Fluorobenzene. This is known as a Bals-Schiemann reaction. Bals-Schiemann reaction. Please check the spelling. Bals-Schiemann reaction. We should be knowing the reaction spelling. If there is a here and there, it's okay. This reaction, when you react it with water and heat it little bit, just heat little bit of heating, it gives you phenol. Anyways, this is not a part of our reaction for today. We just need to know that you can prepare fluorobenzene. That's known as Bals-Schiemann reaction. These are known as Sandmeyer reaction. This is known as Sandmeyer reaction. These two are known as Sandmeyer reaction. These two. This has no name. You can give your name or your miss name, your madam's name here. Let me name it as on my name. This is Alkene reaction. Clear? Okay, let's proceed to the next part. Very, very, very important. Benzene diazonium salts. Various reactions you can do. Let's discuss some of the properties, chemical properties of haloalkanes. The first one is the basis of the nucleophilic substitution reaction. There are two kinds of substitution reactions that we can perform on haloalkanes. One is known as SN1, the other is known as SN2 reaction. I will try to explain first what is SN1 and SN2 reaction, then we will go into the detail of it. Suppose I start with CH3, CH2, CH3. Let's say I have this compound and I have a let's say I have halogen present here, or I have anything present that's, let's say, in general leaving group, Lg. Lg represents leaving group. Leaving group. G represents group. L represents leaving. So this is going to leave with the pair of electron. I can do two reactions, both when nucleophile reacts. Nucleophile reacts. The product obtained, beautiful thing about this reaction is the product obtained looks like they are same. Looks like they are same, but that's not guaranteed. I don't want you to rattle. I don't want you to just memorize that there is something called SN1 and SN2 reaction and this is how it happens. No, you need to understand the fundamentals of it. You need to understand the theory behind it. So we expect that the product obtained after the reaction here, if it is a direct substitution, if you just replace Lg by a nucleophile, it will be SN2 reaction. I will explain you. I will explain every single thing about it. But if you go via something called a carbocation and then you bring in nucleophile to get carbon nucleophile ka bond, where it is, that we have to find out. Then this is known as SN1 mechanism. Then it is SN1 mechanism. We are going to discuss that in very fine detail now. So let's start, everybody. I have seen that, I have asked when I was teaching in IIT Guwahati also, the moment you ask what is SN1 as the SN2 reaction, oh, everybody is in now trouble. Everybody in the classroom will be in trouble. What to answer? We do not know. See this guy. See this guy. I have a very simple and very nice analogy to discuss what is SN1 and SN2 reaction. Although I explained this in words when I was teaching in my previous organizations and when I was teaching in last Akash also, I used to always use this picture to explain what is SN1 and SN2, and that fits the best. This is the very, very, very fine explanation of SN1, SN2 gallery behind that equation. Suppose this is bubbly, this is chubbly, or if you want to give them different names, let's say it is a let me change the color. Yeah, let's say this is cheeky and this is peaky. There are two cats, one is cheeky, another is peaky. So cheeky says, I want to sit on this place, and peaky leaves humbly. Peaky leaves and creates the space free for the cheeky. Cheeky comes and sits on that empty space, on that vacant space. But suppose now cheeky wants to occupy that place and peaky doesn't want to leave. What to be done? Now the cheeky is very adamant that I want to sit on that place. Somehow I want to sit on that place. So cheeky will try to kick away PP. Cheeky will try to kick away Peaky. So Peaky has to get out and then Cheeky will take place. Cheeky will take that place and occupy that place. Correct, everybody? So what I'm trying to tell you, if the reaction follows the first kind of pattern, it will be SN1 mechanism. This is SN1 mechanism and this is SN2 mechanism. If the nucleophile comes, this is the nucleophile. Now let me rename. This cat is a nucleophile and this cat is a leaving group. If leaving group leaves happily, and then nucleophile is invited by the substrate. This is your substrate or your reactant. It is invited by the nucleophile. Please come and take the place and make a bond. Then it becomes SN1 mechanism. See this, a bond has been made again between the nucleophile and the substrate. But if nucleophile wants to come, if the nucleophile wants to come and leaving group does not want to leave, nucleophile has to kick away that leaving group. Forcefully it has to do. So the nucleophile should be strong enough. Are you following, guys? Nucleophile, cheeky, should be stronger than peaky to push her away, so that it can take that place. And then Peaky sadly standing there with a sad face. What has just happened? I didn't realize because she was weak. Peaky is weak here. Okay. Now let's talk about what is SN1 reaction in detail. Suppose I start with R. There is CH double bond CH2. The very first step number 1, will be the formation of, step number 1 is the formation of carbocation. And you need to study where will you form a carbocation. And this reaction will be happening in the presence of HX. HX is H plus and X minus combination. In the first step, we are going to utilize H plus. So H plus will be attacked by the carbon-carbon double bond, So I'm writing H plus. This attacks here. Now I have two choices. Either I get this carbocation or I get the second one. You need to make these two carbocations and then decide which out of the two is more stable. Keep that and then rearrange and discard the less stable one. So out of these two, which one is more stable depending upon what is the R? So R is the same in both the cases, so we can ignore its effect. But 3 and this 2. So which one out of the two you think is more stable carbocation? This carbocation has 3 alpha hydrogens nearby. How many alpha hydrogens? 3. It has how many alpha hydrogens? Just 2. So which one out of the two is more stable carbocation? The top one. This is less stable, so let's immediately discard that. Once you get the more stable carbocation, check if it is possible to rearrange to get the stable structure. In this given molecule, I see that rearrangement is not a possibility. Now you have to bring in X to attack on the most stable carbocation site to form the final compound. This is your SN1 reaction. Do you see that, everybody? This is SN1. People are actually confused with this. This is not SN1 reaction. This is not SN1 reaction. This is addition reaction. This is an addition reaction. I know that majority of the students think that this addition reaction is one of the, this reaction seems to be a nucleophilic substitute. No, you are adding H and X. See this, in the beginning you had H plus, in the last you are having X minus, you have added HX. This is not SN2, SN1 reaction. This is not nucleophilic substitution reaction. This is not that. This is an addition reaction. So I deliberately wanted to take this example to clear the distinction between, or the difference between, an addition as well as a substitution reaction. People, I am sure many of you, majority of you are confused with addition and substitution reaction. This is addition. Don't be confused at all. So let me now pull in what is SN1 reaction. Be very careful in listening to me. So I will be bringing CH3, CH2 since we need to substitute, halogen, we need to substitute halogen. We are discussing compounds of haloalkanes or haloarenes ka reactions. I will be bringing in a nucleophile. See this reaction and this reaction, how different these two are. This is an addition reaction. This is not an addition. This is the reaction that has a background SN1 or SN2 reaction, nucleophilic substitution reaction. So nucleophile is substituting this X here. So nucleophile comes here and kicks it away. If this happens in a single step, that is SN2, but now we are discussing SN1 reaction. So it actually undergoes via step number 1, which is carbocation formation. People are confused because the first step is common in the previous case that we just saw, addition reaction, and here. So carbocation formation. This becomes CH3, CX, CH3 plus. Now you have to hunt for if rearrangement is possible. Rearrange if needed. Rearrange if possible. Once you rearrange, now bring X minus, now you bring nucleophile. Nucleophile will attack and you will obtain a compound CH3, CX, and nucleophile comes here. This is your SN1 reaction. Step number 1, carbocation formation. Second one, nucleophilic attack. The first step is slow step. The second step is fast step. And we know from chemical kinetic perspective, the slow step is the RDS, rate determining step. Do you see any kind of nucleophile participating in this reaction, first reaction? No. So the rate is directly proportional to Rx. Clear, everybody? And it becomes independent of the concentration of the nucleophile. Order 0, order 1 on Rx. It becomes independent of the concentration of the nucleophile. This is extremely important point of SN1 reaction. So if I increase the concentration of the nucleophile, will the rate of the reaction be changed? Not at all. If I increase the concentration of Rx, or if I change the nature of Rx, will the rate of the reaction will change? Yes, definitely will change. Is this fundamental of SN1 reaction clear, everybody? What is SN1? You have to generate a carbocation and then you have to rearrange it, finally make the compound. Now, what are the stereochemical outcomes of SN1 reaction? Let's say you start with RCH, CH, double bond CH. We just have discovered that we will be forming positive charge on this carbon, CH, X here. Once the X leaves, you will be generating RCX, CH3, positive charge here. We need to know what will be the structure of this carbocation. Carbocation is sp2 hybridized. It has an empty p orbital present with it. So it will be written as R, carbon, positive. There is a CH3 and there is a hydrogen present. So this has an empty p orbital with it, because the hybridization of carbon plus is sp2. If it is sp2 hybridized, there is one free empty p orbital, atomic orbital present. Now the nucleophile can come from the top. Or from the bottom. Since sp2 hybridized carbocation is stable, it's a planar structure, nucleophile can come from the top. If it comes from the top, the planar structure will gain the tetrahedral shape once again with the help of a new bond here. Or if it comes from the bottom, there will be this sort of flower made, this sort of tetrahedral structure made. Did you follow this, everybody? Earlier, your carbocation is a planar. If nucleophile comes from the top, this will bend from this will form a pyramid on the bottom. Pyramid here and a new bond here. But if it is the attack happening from the bottom, this is your carbocation stable planar structure. Nucleophile comes from the bottom and it forms a tetrahedral structure like that. Clear? So you can get two type of stereochemical outcome. One, you will observe if you had if you had X here and it was my if you had X here, let's say this is CH3, this was R, this is H. If you have SN1 mechanism going on, there will be two products formed. One, the nucleophile comes where the X was present. This is CH3, this is R, this is H. Or the other one could be the nucleophile on the other side. Nucleophile could be on the other side. So both kind of products are possible. If you see X on the same side, nucleophile on the same side, this is known as retention. Retention. But if you see the nucleophile comes on the other side, this is known as inversion. This is known as inversion. Practically, we obtain inverted product little higher in concentration than the retention product. Theoretically, we should get both of them 50-50 because the chances of attack by the nucleophile from the top and from the bottom, they are half-half. They are 50-50. But here, since this bond has to break first to generate a carbocation, this itself is a slow step. So the nucleophile may not wait for its production and immediately attack on the production, immediately attack via SN2 type and form more of inversion product. Inversion product will be generally little higher in concentration. So it will be nearly 51% or 52% and retention will be close to 49%. So the total makes it 100. Clear hai? Everybody? So you get partial racemization. So the overall answer to this discussion is we obtain partial racemization. So what is racemization? Racemization means the presence of two kind of isomers, enantiomers, two enantiomers. One is if it is R enantiomer and the other one is S enantiomer. If both of them are present 50-50, half, same amount, then it is racemic mixture, 100% racemic mixture, pure racemic mixture. But if one of it is higher in an amount, the other one is a little less in amount, then it is partial racemization process. So SN1 undergoes partial racemization, not full, not complete racemization. Then these are the few points to be noted. First, that it is a two-step process. This number 1 for SN1 does not represent the order, it represents molecularity. This represents molecularity. This represents molecularity. It means in the reaction, RDS, how many molecules are participating in the reaction? It is just 1. So this has molecularity equals to 1. Rate is just dependent upon the substrate concentration and it is independent of the concentration as well as the nature of the nucleophile. So carbocation forms, you have to take it through the rearrangement if at all is possible, and rate determining step is the formation of carbocation. How do we decide which reactant will undergo the fast reaction or the slow reaction? Based on the stability of carbocation. If carbocation is more stable, as the stability of carbocation goes up, the rate of reaction will also go up. Okay. The rate of the reaction is directly proportional to the stability. Rate of reaction will also be directly proportional. How facile the formation of carbocation is based on its own stability and also based on how the leaving group would like to leave. If it would like to leave very easily without any problem, without any trouble, that's a win-win situation. Then it's a win-win situation. Also, polar protic solvent, PPS, polar protic solvent, for example, water, for example, alcohol. We generally use these two type of solvents. They will favor SN1 reaction. And if the nucleophile itself is the solvent or solvent itself is the nucleophile, then that reaction becomes solvolysis. And solvolysis reaction also follow SN1 pathway. SN1 pathway by solvolysis reaction. Now solvolysis ke liye you can use ammonia as the solvent as well as the nucleophile or water or any sort of alcohol, ROH. Solvolysis are always first order, are always SN1 reaction. So you should also know that there is a partial racemization happening, not full racemization. Let's proceed to our energy profile diagram. See, I have told you this will be the energy, potential energy. and this represents reaction coordinates, or reaction coordinate means progress of the reaction. Reaction coordinates. I will be solving some questions also in the end, so you need not go away. You have to complete this session, everybody. You have to watch this up to the end. So reaction coordinates and potential energy. In the beginning, I had Rx that dissociated to form one of the intermediate. This is known as intermediate. Can you name what kind of intermediate is this? What kind of intermediate is this? That's a carbocation. Carbon having a positive charge is carbocation. Now X minus comes and you get Rx. So this is my reaction number 2. This is my reaction number 1. This is my reaction number 2. This is a slow reaction and that's a fast reaction. Clear? So this is my reactant. This is my product. Let's say I bring a nucleophile instead of that. If you are confused with X and X minus, I bring a nucleophile and then our nucleophile is formed. R nucleophile. Okay. So the reactant will have some energy of its own. As it possesses some kinetic activation energy, it will come down to one of the intermediate. Again, it will form some compound. I'll explain you once again. This is my Rx. This is your R bond is just about to break. Let's use dash 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 X. This bond is just about to break. Okay. This is your intermediate R with a positive charge. And here again R is just about to form new bond with the nucleophile. So this is your R with the nucleophile bond formed. This is your product. This is your reactant. This is your intermediate. That's your transition state. These two are known as transition states. So how many transition states do you see? How many transition states do you see via SN1 mechanism? 2 transition states. One is where Rx bond is just about to break. That's step number 1. And the second one, the step number 2, formation of R nucleophile bond. Clear, everybody? This is the energy profile diagram of SN1 reaction. Now we need to know what are SN2 reactions. In SN2 reaction, there will be direct attack. Suppose now I have X present over here, or you can say there is X is leaving group. X is leaving group. This is leaving group. X is leaving group. Now I bring a nucleophile. Nucleophile is so strong here that it does not wait for X to come out and leave behind a positive charge. But this nucleophile has to always attack from the back side. Always have to attack from the back side. This is known as backside attack. Now this becomes a new molecule with a nucleophile bond. Now in the beginning, if you have X present here, okay, this is the X here. Let's say this is my CH3, that's R, let's say that's H. When you react it with the nucleophile, nucleophile will always attack from the back side, and there will be inversion. There will be always inversion. This is known as inverted product. Inverted product, 100% inversion, inverted product. If you start with a chiral alkyl halide, the nature of the configuration will change. R will become S and S will become R. You start from R, R will become S after SN2 reaction. You start from S, you will form R and enantiomer after SN2 attack. This is known as R and SR configurations. I'm sure you know how to calculate R and S, how to figure out R and S. Okay? Clockwise rotation, anti-clockwise rotation by CIP rule. Let's move to the stereochemistry outcome of SN2 reaction. See, we just discussed that you start from Rx and directly there is a nucleophile coming in. Nucleophile attacks from the backside and kicks away and it kicks away X. So you have a direct R nucleophile reaction. Direct, single step reaction. So energy profile should also be, this is my reactant and it forms a product without any formation of intermediate. This is my Rx and nucleophile present. This nucleophile is just about to form bond and X is just about to leave its form. So this bond is going to break, this bond is going to form, and that's finally your R nucleophile. What is this stage called? This stage is now transition state. Is there any intermediate formed during SN2 reaction? No. This is transition state formed. Okay. Now which factors are going to decide will there be any sort of inversion, or will there be SN1 or SN2 reaction? This is the energy profile we have just discussed. In the chemical output, we have seen that we will be obtaining inverted product, 100% inversion, and in the case of energy profile, we have seen that we have one transition form during SN2 reaction. Some points to be noted, guys. This is a single step reaction, direct nucleophilic attack, and X leaves, it's substituted by the nucleophile. Direct. Then transition state formation happens. Attack of the nucleophile is the RDS. So the nucleophile will decide. If it is strong, the rate will be fast. If the nucleophile itself is weak, the rate of the reaction will also be very poor. Okay. Now the rate will be directly proportional to the substrate as well as the nucleophile concentration. Both of them very important. You take a stronger nucleophile, easily substitution will be happening. Molecularity is 2. So there are 2 molecules participating in RDS. The rate of the reaction will be directly proportional to the electron withdrawing groups. Now why do I need that? Suppose I have X to be substituted. I want to generate high amount of positive charge on this carbon so that nucleophile can come and easily attack. I have CH3, CH2, X. I have a CH3, CH, X, and here I have NO2. My question, everybody, you need to answer in the chat box, in the comment box, which one out of the 2 you think will give faster SN2 reaction? Faster SN2 reaction. This is one substrate. Nucleophile is common for both the 2 reactions. Nucleophile can come and attack here, X leaves. Nucleophile can also come here, attacks, and X leaves. Which out of the 2 will give a faster reaction? Number 2 it is. Why? NO2 is a strong electron withdrawing group. Very high minus I effect. Very high minus I effect. So there is mesomeric effect. No, here it is not applicable. Yes, NO2 shows mesomeric effect, but here it is not applicable. This inductive effect will try to create a huge amount of delta positive charge, and it will invite nucleophile better than the first structure that please come and attack on me. I want to substitute halogen by you. Hence, the electron withdrawing groups present increase the rate of the reaction, and that's what I have mentioned here, that the rate of the reaction will be directly proportional to electron withdrawing groups and inversely proportional to electron donating group. So withdrawing groups, these are electron withdrawing groups, the one which withdraws the electron. Now it cannot just be nitro. You can have cyano, you can have halogen, various examples. So let me write, you can have NO2, you can have cyano, you can have halogen. Any group which is present will facilitate the kicking out of the existing halogen. Walden inversion happens and the polar aprotic solvents will favor SN2 reaction. What are those polar aprotic solvents? Example can be acetone. Example can be DMF. What is DMF? Dimethyl formamide. Dimethyl formamide. You can have amide, formamide. You can also have DMSO, dimethyl sulfoxide. Dimethyl sulfoxide. This is known as DMSO. DMSO, dimethyl sulfoxide. This is formamide. Amide means C double bond O, NH2. From formic acid, if you make such kind of molecule, that is known as DMF, dimethyl formamide. This amide is made up of formic acid. Okay, these many solvents, but generally we use these three in our particular discussion. I have brought to you a graphics which is basically created to show you how SN1 and SN2 reactions are observed, or if you want to pictorially depict on a paper how you should do that. Suppose there are four groups present. There are four groups present in the substrate. One of it is labeled as leaving group, the something which leaves and invites a nucleophile. If leaving group leaves happily and leaves behind a positive charge, that's carbon plus. This is carbocation, and that is SN1 mechanism. Nucleophile can attack from the top because there is an orbital present, atomic orbital present. There are two lobes. The lobe can receive the electron from the top or from the bottom to form a bond. Now, either you get this attack or you can get this attack, the top side attack or from the bottom side attack. So there are two products possible. Both of them would be present, but the ratio will not be 50-50. Inversion product will be little higher in compared to the retention product. But if you directly substitute, do you see that some sort of pentavalent carbon is present? Actually, there are not 5 bonds. One bond is just about to form. I'm writing small f. This is about to form. This bond is about to break. Leaving group is just leaving and the nucleophile is just coming. And then finally a bond forms. This is inversion product. This is inversion, and that's retention. That's retention. Clear, everybody? Clear? See this, the position of these groups, relative position of these groups is not changed. Wherever nucleophile was, wherever leaving group was, nucleophile has come to the same place. Wherever this dot was present, this element, this group was present, it is still present on the same side. Wherever these green and the yellow dots are there, these groups are also present on the same place where they were originally present. But here they are relatively changed. Here their spatial arrangement is changed. That spatial arrangement is known as configuration. Okay? Alright. Now compounds which will not show SN1 and SN2 reaction, very tricky question. Number one, if you have haloarene, will it undergo SN1 or SN2 reaction? Answer is no. Why? Because there is a double bond character present due to the delocalization of these bonds, these electrons, and you will generate a double bond that becomes very, very challenging to break it. Very, very challenging to break the double bond. So you have double bond character here. Let's move this double bond here. You get a negative charge. Double bond, double bond. Breaking this double bond is very, very difficult. So hence, number one, this will not show SN1 or SN2 reaction. Second case, similar example, CH vinyl halide. Vinyl halide, due to the double bond character once again, they will be, this is the resonating structure. This is also a resonating structure, negative. CH negative, CH X positive. This is resonating structure. Double bond character, again, it's not possible. The third one, cyclohexane, but on the position 1 and 4, position number 1, 2, 3, 4, it is having a substitution here. Suppose there is a Br present or halogen present here. So here also you cannot do any sort of substitution because this carbon is very hindered, is known as bridgehead carbon. And creating carbon positive on bridgehead carbon, that's very difficult. Why? Because carbon plus is sp2 hybridized, having 120 bond angle. But then this is sp3 hybridized carbon having a ring. Once you try to create sp2 hybridized, this ring cannot flatten. This ring cannot become planar molecule. It's impossible to happen. Also, this is of 1, 2, 3 tertiary halide nature, which is not a favored compound for SN2 type of reaction. So SN1 is also not possible and SN2 is also not possible. Remember, these three examples are very important. Don't do any sort of SN1 or SN2 reaction here. Okay, now the points that you should note is that iodide is a good leaving group as well as a nucleophile. Suppose I want to do this reaction RX I want to substitute this Rx and reacting it with NaI to produce Ri. To do R, to do yeah, let's say I want to do this reaction. Or the other pathway is, suppose I want to do this reaction first. I want to have, instead of that, okay, let's say instead of taking NaI, that's Finkelstein reaction basically, I want to take KCN. So I will be obtaining R KCN RCN. The second stage is, let's say, Rx, reacting it with Ki first to get Ri. Rx reacted with Ki to get Ri, and then reacted with RCN or KCN. RCN is obtained. You need to tell me, out of the two, number 1 and number 2, which one is a better method? Which one is a better method? Let me put it as chlorine so that the comparison becomes easy. Tell me which method you think practically is better. Second method is practically better because here iodide is a better nucleophile. Iodide is a better leaving group also. So you do the reaction in 2 steps, you will get a better yield of this compound. Rather than doing one single step reaction, you will get less yield of the compound. So iodide is a good leaving group as well as is a good nucleophile also. So in the first stage, here it is acting as a nucleophile and here it is acting as a leaving group. The neopentyl halide also will show. Neopentyl halide is this compound, that's X here. Although it looks like that's primary alkyl halide should be favoring SN2 reaction, but due to this hindrance of R group, the SN2 reaction also becomes very sluggish, and also SN1 reaction shows slow nature. You can obtain a positive charge here because this halogen is just lost. You will obtain CH2 with a positive charge. Then you can do this methyl shift. Let's do this methyl shift. Methyl goes on this carbon and you will obtain CH3 with a CH3, CH2, CH3, and finally carbocation is formed here after rearrangement. Once the rearrangement is done, then you can bring in a nucleophile to satisfy this carbon positive, forming a covalent bond. Remember, neopentyl halides, they show SN1 reaction but very slow. The third point is AgNO3, AlCl3, they are also they are the candidates which removes halogen. They are all known as halogen abstractor. Halogen abstractor. They abstract halogen. Okay. For example, I have Rx, react with any one of these, AgNO3. Generally, we use AgNO3. You can also use AlCl3. You can also use SbCl5, etc. They are going to produce R plus, and they can form AgCl precipitate, or they can form AlCl4 negative. They can also form SbCl6 negative. Suppose I was using X as halogen. If I was using X as chlorine. Make sense? Okay. The solvolysis I have already discussed with you. I have R of X. If I have Rx, I want to do reaction with water, or I want to do reaction with ammonia, or I want to do reaction with ROH. They all will fall into the category of SN1 reaction. They are solvolysis. Clear, everybody? Okay. Now let's do some comparison of SN1 and SN2 reaction. Substrate. What kind of substrate does SN1 like? It like tertiary alkyl halide over secondary over primary alkyl halide. It want less crowding, less steric crowding. So primary alkyl halide is preferred over secondary, is preferred over tertiary. Okay, the nucleophile here should be weak in nature. So that it gives a chance to the alkyl halide to produce carbon positive. This should be strong enough. Generally we use neutral nucleophiles over here. For example, water, for example, ammonia, for example, alcohol. I have repeated this point many times. Now you should not make a mistake. Here generally we use negatively charged like OH minus, we use NH2 minus, we can also use RO minus. Majority of the time we will be using RO minus. The leaving group here also should be a good leaving group. Therefore, Ri will be giving a better good reaction, Ri compared to RBr, compared to RCl, and compared to RF. And here also the same order. Here also the same. Solvent here, polar protic solvent. Polar protic. For example, water. For example, alcohol. But here polar aprotic solvent. Polar aprotic solvent. For example, DMF, acetone, DMSO. DMF, DMSO, acetone. These are the examples. Make sense, everybody? Comparison done. Let's proceed. Now we need to, this table is from your NCERT. You can now easily pick that. If you use NaOH or KOH, what will be the nucleophile? It is HO minus. The substitution product, R nucleophile will be ROH, and the compound formed would be an alcohol. So I am explaining the first reaction, how to imagine that. RX is treated with NaOH or KOH. OH minus is the nucleophile which will attack here to obtain ROH. That's alcohol. This is pure SN2 reaction. This will be SN2 reaction. This will also water, SN1 reaction, again SN2 reaction, SN2 reaction, SN1 reaction, SN1 reaction, SN1 reaction, SN2 reaction again. This will be again SN2 reaction, SN2 reaction, SN1 reaction, and all these reactions. So I want to discuss a few of those reactions. We can start with E1 reaction. In the end of the session, I will be bringing to you many examples, I will also give you some homework. Don't worry about that. What is E1 now? E1 represent, the second part of this talk is representing elimination reactions. Now try to understand, if I have this molecule CH3, CH2, Cl, if you remove halogen, the carbon which contains halogen is known as alpha carbon, and the neighboring carbon is known as beta carbon. I am repeating. The carbon which contains halogen is known as alpha carbon, and the neighboring carbon on the left, right, upside, downside, wherever it is present, it is known as beta. Remove alpha halogen and remove hydrogen from beta. Once you do that, a combination of HX is done. So you are going to generate alpha carbon double bond beta. I am explaining. The product obtained will have a double bond between alpha and beta. If it is happening directly, then it is E2. If it is happening via carbocation, it is E1 mechanism. So E1 and SN1, they are similar mechanisms. But here in E1, we form an alkene. In SN1, we form substituted product. So like here, we will be discussing E1 reaction. So first of all, you need to remove this compound and generate a carbocation. So CH3. Once you have generated a carbocation, obviously you need to, what do you need to do? What do you do to carbocation once it is formed? We rearrange that. So I have a hydrogen present. I will be trying to move it via hydride shift to obtain more stable carbocation, that's CH with a positive charge, and that has got a more number of alpha hydrogen than the previous one. Finally, I will now take out beta hydrogen from either side. This beta and beta dash, both the sides they are same. Minus beta hydrogen. Beta hydrogen is lost. So you will obtain CH2 double bond CH3. This is your alkene formed. And the alkene formed will be either of the two type. One is known as Setzef alkene. Setzef alkene is the one which has higher number of high alpha hydrogen around carbon-carbon double bond. This is your framework. You need to check whether the number of alpha hydrogens are more or less. That will be the product. Second one is known as Hofmann product, Hofmann alkene. Hofmann alkene is the one which has less alpha hydrogen around carbon-carbon double bond, but even will result into Setzef alkene. Can you tell me in the comment box how many alpha hydrogen do you see here in this compound, in this product? How many alpha hydrogen, everybody? How many alpha hydrogens are there? How many? Count and tell me in the comment box. Now, what is E2? I was telling, if you have carbon containing, let's say this is CH3, let's say this is my CH3 with a CH, halogen is present here, this is CH2, and then hydrogen is present here. The carbon which contains halogen is known as alpha, and the carbon neighboring carbons to this alpha is known as beta, and this is also beta. Since both of them are same, so beta. You will be removing these two together to get this compound, that's CH3, CH, double bond, CH2. But there is only single condition that we need to understand. The reaction condition will be, it is a beta hydrogen elimination when halogen and beta hydrogen are anti-periplanar to each other. Now, what's the meaning of anti-periplanar? They should be present in their opposite planes. Anti-periplanar should be anti-periplanar. Okay, should be anti-periplanar. Let me show one diagram to help you in understanding what does anti-periplanar mean. Suppose I show that this hydrogen is present in the dash, and this is present in the form of wedge. This is okay, perfect. I have one group present here. Let's say this is the hydrogen, and this is chlorine. Okay, very good. Anti-periplanar. Now I am going to number these hydrogen as number 1, number 2, number 3. This is my alpha carbon. Any doubt? This is my alpha. I need to take out this chlorine for sure. But the hydrogen from the beta carbon should be anti-periplanar to it. So which one out of 1 and 2 should I take out? Which one out of 1 and 2 should be taken out? Tell me in the comment box. Which one out of 1 and 2 should be taken out? Can I take 1 and 2? No. Can I take this one, hydrogen number 1? No. I have to take hydrogen number 2 because it is present in its opposite plane. So the compound found would be CH3, C with a hydrogen double bond, and there is a hydrogen here. This hydrogen number 1 is gone, this hydrogen number 2, this hydrogen number 3. Sir, why are you not showing this dash and wedge projection here? It's a planar molecule, ra. It's a planar molecule, carbon-carbon double bond, sp2 hybridization. Understood what is E2 mechanism? If the elimination is happening in a single stage, it is E2 stage. It is E2 mechanism. The reaction that involves metals also we need to know. What are metals? For example, I react Rx. For example, I react Rx with metal, Rx with sodium. I will take two of these. I'll take two of these so that it forms RR. This is known as Wood's reaction. This is known as Wood's reaction. When you take this, it happens via radical mechanism. Radical mechanism. So it's a doubling of carbon-carbon. The final compound obtained is an alkane of double the number of carbon atoms you had in the beginning and at a cost of halogen. Halogens are lost. Okay, now we need to discuss some of the properties of haloarenes. What do they do? What are their properties? So we can do lots of reactions of haloarenes. Haloarenes, basically we will be having one very important point before we discuss. There is halogen present which can participate its pair of electron in the resonance and can have a double bond character. So hence it is not a good candidate for SN2 type of reaction. Also not for SN1 kind of reaction. So what we need to do instead, what kind of reactions we do? So we need to understand that in the presence of electron withdrawing groups, we can do that SN2 type reaction very easily. SN2 type reaction. So let me go back and explain to you how do we actually do that. So this is the double bond which causes a problem, which will cause a problem in the substitution. But you can use NaOH at a very high temperature and very high pressure. High temperature, high pressure. This is known as Dawes process. This is known as Dawes process, and you can prepare phenol from this. You can prepare phenol from this, but this reaction is very challenging. Dawes process is the name of the reaction. It is done at approximately 623 Kelvin and 300 bar pressure. Very difficult reaction to do. How is it happening? At this situation, I am increasing the nucleophilicity of this NaOH, and that could easily kick out halogen from the existing compound. Otherwise, in the normal condition, SN2 reaction is not very easily possible. So our aim was either to increase the nucleophilicity of NaOH or increase the electrophilicity of this compound. So I chose to increase the nucleophilicity by increasing high temperature, by making high pressure, but I don't want to do that. What other way you are left with is to increase the electrophilicity of this haloalkane. If I substitute it with electron withdrawing groups, what will happen? This carbon will experience some electron density, loss of electron density, and then NaOH can easily come and attack here on the center. I'm repeating. The electron withdrawing group will enhance the positive charge on this carbon which contains halogen. The carbon which contains halogen is our objective. We need to replace this halogen, correct? So this carbon should carry high amount of positive charge. That can be done in the presence of NaOH, but having rings substituted with electron withdrawing groups. How it happens? Let's discuss that. If you attach electron withdrawing groups, then the positive charge on that center will enhance. I'm going to show you one example. Rest will be understood to you, very easily understood to you. Suppose I have para-substituted nitro compound. On the para position with respect to halogen, I have a nitro compound present. So this nitro is, we know it's minus M effect, minus M group. This will pull out the electron density from the ring. This goes here, this goes here. So there will be pi-pi conjugation. This generates a positive charge in the center. So you draw the resonating structures, you will experience that this carbon which has halogen has now got a positive charge. The positive charge on this carbon. Okay, this positive charge is now on this carbon. Here, let me write it inside. Yahan, aise. Positive charge. More you practice organic by writing, you will become champion. All those students of mine who have studied from me, they all say that, sir, organic is the simplest subject ever we came across. Simplest subject. Just because they have practiced a lot. They have practiced, and practice makes everybody perfect, not just the men. Practice also make women also perfect. You should know that. So this is the resonating structure. Now do you notice that this carbon has got a positive charge? Now OH minus, which was wondering earlier, this carbon does not have enough positive charge. Should I go and attack or not? It says no. Attach one electron withdrawing group. Now it's very easy for me to attack because I can form a bond. Now I can form a bond. I need not kick out X. I need not kick out X. I can just form a new bond to satisfy the positive charge, negative charge. They are going to form a bond. Very easy. Now, if it happens, now what is going to done? What is going to happen? There is this nitro compound. Let me have a halogen here and nitro on the the second para position, ortho position. Double bond, double bond, double bond. Now I bring OH minus from here, from outside, attacks on the center. This negative charge will be in the resonance. This negative charge will go here, will come here, will come here. This negative charge eventually will reside on this center, on this carbon. So I can write one resonating structure which involves the delocalization of this double bond, dash, 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 dash. This negative charge is in resonance. There is a halogen present. And remember, there is this halogen present. Halogen is present here. NO2 is present here. And now you have brought in OH. You have brought in OH. OH aa chuka hai. OH aa chuka hai. This is known as Mesenheimer complex, Mesenheimer intermediate. Now, the moment this pair of electron which is present here on this center, right, this center, this negative charge, when it wants to come back, this negative charge present here, when it would like to come back, see, this is the structure NO2, this is X, this is OH. This is OH. When this negative charge wants to come back and tries to form bond, it has to either kick out X or it has to kick out OH minus. OH minus cannot be kicked out because X was the group we wanted to substitute. X leaves and you obtain a compound OH in the place of halogen. This reaction becomes now pretty easy when you substitute haloalkane with haloarene with electron withdrawing groups like nitro, like cyno on ortho or para position. Remember, ortho or para positions. If you try to see the effect on the meta position, that's never going to work because there will be no mesomeric effect, just a poor inductive effect of nitro group will be in play. Okay. I have a question. Chalo, I think I have included that on the slide. This is, I was explaining to you, I have brought to you a graphic also. You can look into this graphic. If possible, I will post the HD file also of this graphic in the comment. So this is my nucleophile. Suppose I bring in a nucleophile. I can substitute that fluorine here. This fluorine can be substituted by a nucleophile, which is otherwise very weak nucleophile. How am I increasing the how am I facilitating this reaction? By increasing the electrophilicity of the haloarene ring, substituting it with electron withdrawing group. So there is a mechanism number 1 that is known as via addition elimination method. You can substitute the halogen of the aromatic ring of haloarene ring via addition elimination method. Addition elimination method. So first you will be adding the nucleophile, then you will be eliminating the leaving group present. So let me go back and explain to you. See here, initially I have done the addition. This is the addition of OH. This step is known as addition step. And when OH minus is present and X is leaving, this is known as elimination step. So if you substitute benzene having halogen with electron withdrawing groups, now this will prefer substitution SNAR. This is known as SNAR. Nucleophilic substitution reaction on aromatic rings SNAR via some sort of SN2 nature, but via addition elimination pathway. So can we do via elimination addition pathway also? Yes, that can also be possible. That is known as arene mechanism. So before that, let's discuss some of the other points. That step number 1 is the RDS. Step number 1 is the formation of negatively charged species, the Mesenheimer complex. So you make the negative charge compound here, and then nitro is present and X is present. Still, X is still there. X is still present. I did not touch X at all. So this double bond which is in the resonance, this double bond which is in the resonance will help us in explaining. There's a double bond here, there's a double bond here, X here, X brings in the double bond here inside, double bond, a double bond, right? Now fine, got it. Double bond and double bond, and then you have brought in this in the X here and OH here. X and OH, both of them are present, and the negative charge is in the conjugation. This carbocation stability will decide. This carbocation stability will decide whether the compound will actually form or not, right? If carbanion, sorry, not carbocation, carbanion is highly stable, then the reaction will proceed nicely. If not, then reaction will not proceed. That the purpose of installing the ring with the electron withdrawing group is also justified here. Negative charge is basically stabilized by having electron withdrawing group. So how do we stabilize carbanion? By attaching electron withdrawing groups. This is a good situation. How do you stabilize carbon plus? By having electron donating group. This is also a good situation. What do you have here? A negative charge species and electron withdrawing group present on the ring. So this becomes the most stable structure. So far X has not left. X has not left the system. So will the strength of CX bond will decide the rate of the reaction? No. Hence we say that even if this X is fluorine, if the X is fluorine here, so the rate of fluorobenzene will be the highest. This looks little bit chatpata atpata, है ना? Chatpata तो नहीं atpata. That the rate of Haloarene is the highest. And you might be thinking, sir, how is that possible? We also know that this bond is the weakest, so it should give us the fastest reaction. Make sense? It should give us the fastest reaction. But remember, we are not breaking this bond in the rate determining step. Rate will be decided by the step which involves the breakage of the bond, rate. So rate depends on the stability of the carbanion not on the bond breaking stability. Now I see that there is this negative charge which I want to stabilize, with the nitro here. Do you think that fluorine and OH, if this is one of the molecule formed from fluorobenzene, this will be more stable? Why? Minus M effect of, as well as minus I effect of nitro, plus minus I effect of fluorine, which is the best among all the halogen, will also help in stabilizing carbanion. Makes sense, everybody? Is this clear? Is this clear, everybody? All right. Okay, good. So it also says that the rate of the reaction, this is very important point. The rate of the reaction will be directly proportional to the number of electron withdrawing groups that you have. For example, here nitro groups. If you have 2 nitro groups, the rate will be faster than having 1 nitro group. If you have 3 nitro groups, the rate will be fastest. So I have a comparison question here. Compare the rate of the reaction. The first one, I have just the fluorobenzene. Then I have, you need to answer this question in the comment box, number 1. Then you have nitro attached on the ortho position, number 2. Then I have third, nitro present on the meta position. Then I have fourth. See, I brought to you the entire haloalkane haloarene chapter, which is helpful for you, not just for your board examination, but for your NEET and JEE examination also. Okay, chalo और एक ले लेते हैं. Let's have one more fluorine here and one more. और भी ले लेते हैं. 5, मजा आता है यार. 6 और लेंगे, और भी लेंगे. 7, चलो बहुत है. This is enough. Okay. Okay. This was 6, this will be 7, this is 8. Okay, we have to answer this order, compare the rate of the reaction towards SNAR, nucleophilic substitution reaction on AR. Nucleophile is the same for all of these. Okay, chali, next part. ESR, we have chlorobenzene. Now we want to do electrophilic substitution reaction. That means we need to introduce an electrophile for this process. Electrophile leke aana hai. So one reaction that we can do, I'm sure you can see that. Now I can bring let's say I want to do another chlorination. FeCl ले लेते हैं, FeCl3 or FeCl2. Then I will be getting two compounds, one ortho and para isomer. This is major. This is major. Para one is always major. Then I can do Rx in the presence of AlCl3. Right? So this will be Cl here, R, and I can have para product. Para is again the major one. Para, major again. This is known as Friedel-Crafts alkylation. I can do RCOX in the presence of AlCl3. This is known as Friedel-Crafts acylation. I can have chlorine already present, and on the ortho position C double bond O R, plus on the para position Cl, para. Okay. What else we can do? We can also do reaction with NaNH2. We can have aniline made from here. What else we can do? We can treat it with NaOH at a very high temperature and high pressure. We can make phenol. Lots of reaction can be done. Lots of Dawes process. Right? We can do sulfonation. We can do nitration also. Suppose I do the nitration with concentrated HNO3, you will obtain ortho and para product once again. You can have NO2 plus para. Various reactions can be done. Various. You can do sulfonation, concentrated H2SO4, or we can use oleum. You can do sulfonation. Again, on the ortho as well as para. Para will be major. So many reactions that we can do. Clear, everybody? Let's proceed. Now we have the mechanism that was explained to you: addition, elimination, and then elimination, addition method. So we have chlorine present here. Let's say I have a chlorine, and you remember every carbon has hydrogen also present on it. Hydrogen. Now when I react it with a strong base, what will strong base do? The base will be preferring the hydrogen present to the next carbon of the halogen containing carbon. So when it leaves here, it forms benzyne. You might have heard of this kind of intermediate known as benzyne. This is known as benzyne. In short, it is known as arine. This is one of the intermediate, just like carbocation, carbanion, radicals, carbene, nitrene. This is also known as a benzyne. Once now NaNH2 comes back again, this will form negative charge and NH2, double bond. Now you can bring water to neutralize this. Clear, everybody? Okay, good. This is via elimination addition method. You first have eliminated chlorine. Please see that you have eliminated chlorine, then you have added NH2. Okay. Now we will be doing some reaction with the metals. Wood's reaction I have already discussed with you. Suppose I use Rx, which is alkyl halide. reaction with sodium, another alkyl halide, another alkyl halide, another alkyl halide. Then this will be AR. This is ARX. This will be aryl halide. This is known as aryl halide. If R and AR, this forms the product, then it is known as Wood's fitting reaction. Suppose I bring in ARX with sodium plus another ARX. ARX क्या होता है? What is ARX? Aryl halide. The product formed as a result of this reaction will be AR. Right, everybody? Understood? Good. Now, I have brought to you some questions. We will be spending some amount of time in discussing whether we have understood SN1, SN2, E1, E2 or not. Okay? पढ़ते तो सब हैं, everybody study, but how many of you have understood? That is the question. See, the first question given you here is PHS minus Na plus. This is the nucleophile. Nucleophile will attack either here or it will attack here. We have seen that the nucleophilic attack on aromatic halide compounds are not possible. So our choice is this. And here the stereochemical outcome due to this pure SN2 reaction should be inversion. Let's check where is Br gone and you have brought PHS. PHS is present in only option number 1. Here also it's present, but the stereochemistry is the same. But we want inversion, and inversion has happened in the option number 1. Your answer should be option number 1. Clear? Now, second question, it says a solution of plus 2-chloro 2-phenyl ethane. 2-chloro 2-phenyl. Phenyl is represented as pH, correct? So this is my carbon number, let's say 1, this is my carbon number 2. It says phenyl ethane is produced. Phenyl ethane means it will be CH3 and it is number compound number phenyl ethane. So this will be phenyl, this is CH3, this is CH, and there is one chlorine also present. So this will be now a compound which seems to be chiral in nature. Yes, it shows plus sign. It's a chiral compound. Now I want to do a reaction on this with SbCl5. SbCl5, and we looked at SbCl5. What does it do? It's a halogen abstracted. It will abstract this halogen from here and leave behind a carbon positive charge. It will create a carbocation, and that carbocation will undergo further attack in the presence of a nucleophile. So the answer should be option number 1, not option number 1. It should be carbocation, option number D. Is that clear, everybody? Option number D. SbCl5 is a halogen abstractor. Next question. What is the major product obtained in the following reaction? So you have ammonia dissolved in ethanol. So ammonia will be doing solvolysis. And do you remember solvolysis happens via what kind of mechanism? SN1 mechanism. SN1 mechanism. So this substitution of bromine is not possible. We will be doing it here, and that's all. And then the option number which is the answer? Oh, option number C is the answer. Direct answer, CH2 NH2. Very good. Next, following is the substitution reaction in which Cn replaces Cl. Cn replaces Cl. So Cn is about to replace this and Cl is kicked out, so that you get RCN. To obtain propane nitrile. Propane nitrile means 1 carbon, 2nd carbon, and 3rd carbon. 3rd carbon is inclusive of nitrile. From RCl, which should be the RCl ka structure. What is the structure of RCl? See, one of the carbon is coming from cyanide. So I think I should start with these two, R and X. So Rx means it should be chloroethane. You react CH3, CH2Cl plus KCN. It's ionic compound, so it will form carbon-carbon bond, direct SN2 mechanism, CH3, CH2, and then Cn. This will be the compound formed. That's propane nitrile. So option number 1 is the right answer. Chloroethane. That's the right answer. Good, everybody. Now, which compound undergoes a nucleophilic substitution with NaCN at the fastest rate? At the fastest, लिख देते हैं, fastest rate. Fastest rate. Out of these four, which will be the fastest rate? So, NaCN, since it is a negatively charged nucleophile, it will prefer SN2 reaction, and SN2 prefer primary Rx. Let's figure out primary Rx. Is this primary Rx? Yes, this is primary alkyl halide. Is this primary? No, this is secondary. So option number 2 cannot be the answer. Option number 3, is it primary? Yes, it's primary. Option number 4, is it primary? No, this is also gone. So out of 4, we have eliminated 2 options. A and C. Out of the 2, which one has less crowding around CBR center? This has less crowding. It has a little more crowding. So option number 1 is the answer. As the steric crowding increases, rate of the SN2 will also decreases. Okay, which of the following alkyl halide will undergo rearrangement in SN1 kind of reaction here? So here, let's break this halogen. Let's break this halogen. Let's break this halogen also, and then see which one will undergo SN1 or rearrangement. This will generate a carbocation CH3, 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 CH, positive charge, and CH3. This will move here. So methyl shift, yes, it will undergo rearrangement. Here, there is a hydrogen present here. So you generate a positive charge on the center. There is a hydrogen and methyl. We will always be picking up hydride shift first. Yes, there is a rearrangement possible here. In this case, there will be hydrogen, another hydrogen present here, and the positive charge is generated here. So there will be hydride shift and then resonance. Yes, there is a resonance possible here. Option number D is the answer. Okay, whenever you people are solving this question, pause the video, solve your question, come and match. Okay, great. The rate of SN2 will be negligible in which of these following options? This is my secondary alkyl halide. Yes, it could be possible here. This is also secondary alkyl halide. Yes, it's a good chance. And this is also secondary alkyl halide. There is a good chance here. And this is a tertiary alkyl halide. Tertiary alkyl halide, and on top of it, this is a bridgehead carbon. So I told you SN1 and SN2 reactions are not very good in such kind of a bicyclo compound. This is cyclic compound, bicyclo, fused rings. These are the two bicyclo compounds. Okay. Identify the rate of the dehydrogenation in which of the following compound when allowed. So identify the rate of the dehydrogenation. Dehydrogenation to wait a minute, I think I need to do some change. It should be dehydrohalogenation. Let's change this. Dehydrohalogenation, so that we can remove H and X in the following compound when allowed. So in the first compound, this is my alpha carbon which has a bromine. This is my beta, this is also beta, this is also beta. We need to remove hydrogen from the beta carbon. So the compound formed from the first one will be CH2, double bond with a C, and there is a CH3 and a CH3 present. Check please. This will be the compound obtained. How many alpha hydrogen does this have? 3 from here, 3 from here, total 6 alpha hydrogen. Okay. Now here, if I form an alkene from here, this is my alpha carbon, this is beta carbon. So carbon CH3 will have CH double bond CH2. Clear everybody? So here from compound number 1 to compound number 2, the number of alpha hydrogen seems to be reduced from 6 to 3. So first one will be going the faster reaction than the second one. In the third one, you will just obtain no alpha hydrogen at all, 0 alpha hydrogen. Therefore, this will undergo very slow reaction. So 1, 2, 3 should be the order. Option number 1 is the answer. Clear everybody? Which of the following alkyl halide undergoes even reaction with the fastest rate? Even reaction. That means we need to form a carbocation. That carbocation should be stable enough. Now, in this first case, Rx, leaving of Rx, leaving of Rx, leaving of Rx. All these compounds are the same, exactly the same. So which one will form a carbocation the fastest? The one which has the best leaving group. Iodide is the best leaving group. Option number 4 is the answer. Okay, for the following reaction, there is this reaction going on, number 1, and this reaction which is going on, number 2, this reaction number 3. This is the NEET 2016 question. I want you to identify the nature of the reaction. The first one seems to be elimination reaction, right everybody? Because I have eliminated bromine and hydrogen from here. The second one seems to be substitution reaction. Third one seems to be addition reaction. So elimination, substitution and addition. Elimination, substitution and addition. Option number C is the answer. Okay. Replacement of chlorine of chlorobenzene to give phenol requires drastic condition, but chlorine of 2,4-dinitrochlorobenzene is readily replaced by. So it's comparing planar simple chlorobenzene with 2,4-dinitrochlorobenzene. It undergoes better replacement of chlorine, easy replacement of chlorine, but this will be undergoing slower replacement of chlorine. Why? What's the reason? What's the answer? NO2 will make the ring electron rich? No. NO2 withdraws electron from the meta position? No, not again. NO2 donates electron at the meta position array? No. NO2 withdraws electron from ortho and para position? Yes. And hence it creates extra amount of positive charge and make it more reactive. Clear everybody? Okay. I have given to you now another sheet of summary. You can just have a look at SN1, SN2, even E2 reaction during the time of close-up of finishing up this session. You can just go through all these things. I have written down what about mechanism, one-step mechanism, two-step mechanism, comparison of SN1, SN2, E1 and E2, comparison of SN1, E1, comparison of E2 and SN2 can also be done. Remember, one question from this table itself is one question is fixed in your examination. They can either directly ask you to write some features of SN1, SN2, or they can ask you to compare E1 and E2. Remember to write examples also. Okay, now I have this SN1 pictorial diagram once again. I have discussed completely with you. You have a leaving group, nucleophile comes in, rate is directly proportional to the alkyl halide, new nucleophile comes, there is a racemic mixture obtained which is partial. This is partial racemization happens, leaving groups comes out. The step number 1 is the slow step, that is RDS, and it has a empty p orbital present because of the carbocation sp2 hybridization. Second step is the nucleophilic addition, that's fast reaction, and it's of no use to us because the rate will be decided by how fast the ionization happens and how for the stability of carbocation. This is the energy profile diagram. Step number 1, step number 2. Similarly, this will be your SN2 mechanism. SN2 is a direct attack and then product inversion of stereochemistry. If you start with R isomer, your product will be S isomer. If you start with S isomer, your product will be R isomer. This is the energy profile diagram. Only one transition forms here, transition state forms here, and depending upon the stability of depending upon how strong the nucleophile is, the rate of reaction will also be changed accordingly. These are the few questions I am giving you for your practice at home, everybody. I hope you will be able to solve these questions now. Please answer your questions in the comment box so that you can get your answers checked by me and also from your fellow viewers. That's all for today, everybody. I think I have brought to you more than enough from Haloalkane Haloarene chapter. You absolutely need not to read anything else apart from your NCERT plus this your lecture today. NCERT is not a sufficient textbook to understand organic chemistry. This is I can say it to anybody because organic chemistry is not explicitly written in NCERT. You need to understand it from a mentor. I think I was able to explain almost all the reactions. I brought many other reactions from beyond the scope of NCERT also today. It will be helpful for your NEET as well as JEE mains examination. I'll see you in the next class, guys. Till then, stay safe and goodbye. This is your teacher, Dr. Lakshya Kathuria.